Hello, in this video we will look at electromagnetic induction. So there you go, remember the title, Electromagnetic Induction. Okay, when a conductor cuts magnetic field lines, an EMF is induced. So I'm going to draw some crosses here. These crosses represent a magnetic field going into the board. Okay, so they're at right angles to the board, going in like that. Okay, and on here I'm going to draw a conductor. So this is a conductor, maybe a piece of aluminium or steel or something like that. Now it's going to have to move, because it's not going to, without moving, it's not going to cut any of the field lines, and it's not going to produce an EMF or a voltage, a potential drop across the two ends. So let's have the velocity of it acting on that. So we're going to move it with a velocity v in that direction, cutting the magnetic fields perpendicular to them. Okay, now what's going to happen? Now in a conductor, the thing about conductors, metals mainly, is that they have free electrons, and then those electrons can move. So there you go, draw a couple of electrons E. So you think about it, those electrons are moving at right angles to a magnetic field, and as we know before about a force on a magnetic field, you find that the force on an electron is equal to force on an electron moving in a magnetic field is equal to BeV. So that's what you'll feel a force. And in fact, if we look at Fleming's left-hand law, so therefore if the electron's moving in that direction, okay, you'll find that the current, the conventional current, flows in that direction, and with the magnetic field pushing down, you'll find it'll feel a force, and that's called that Fm. So the magnetic force Fm is in that direction on the electron. So we could say the magnetic force is equal to the magnetic field strength B, or magnetic flux density, times the charge on electron E times the velocity V. Okay, so that's what it'll feel. It'll be a force out in that direction. Now, what's going to happen is, if you've got electrons moving to that side, you're going to have a build-up of negative charge on that side. And if you've got a negative charge on that side, you'll feel that you'll get positive charge building up here. Okay. Now if you've got negative charge on one end and positive charge on the other end, you'll get an electric field. Okay, given by the letter E. E is the electric field. And if you've got a charged particle in an electric field, a charged particle or an electron will feel a force. And the force, due to the electric field, is equal to the electric field strength, which is E, times the charge, Q. In this case, the charge is on the electron, so therefore the force due to the electric field is equal to the electric field strength times E. Now, let us say that the conductor is of a length L. Okay. Now, and we'll say that the EMF induced is equal to, let's say the EMF induced is equal to V. So, induced EMF is equal to V. Now, at a certain point, at a certain amount of time, you'll find that there becomes equilibrium. You find for a given electron, it will feel the so obviously got the electrons more at that end. Okay, for a given electron, somewhere in the conductor at some times, it'll feel a magnetic force Fm acting in that direction, of course, because it's negative charge, it will feel acting in the opposite direction at some stage when it's all settled down, an equal and opposite force, rather, which would be the electric field, the force of the electric field. So they will be in equilibrium. So you could therefore write, quite justifiably, that you'll get the magnetic force, Fm, will be equal to the electric force acting on that electron. Okay, now, what happens therefore, we'll move across to here, so we'll take this up to there, the magnetic force is equal to the electric force, they become equal in equilibrium, therefore you'll find that here, Fm, which is magnetic field strength times the charge in electron times the velocity at which the conductor is moving, is equal to the electric field strength times the charge in electron. Now quite clearly you get the charge in electron cancels out to give you BV equals E. So therefore the magnetic field strength times the velocity is equal to the electric field strength. Now you can think of wires very similar to parallel plates, but you think, well, they're not parallel plates, they're very, very thin wires, but compared to the size of an electron, they're very, very wide, like parallel plates. So therefore, also it comes to the idea that the electric field strength due to parallel plates is equal to the potential difference between each end, V, voltage, divided by the length. So therefore, we can have B times V is equal to the voltage induced divided by the length. And therefore, finally, and I'm going to rub us a space just here, we'll find from there, we will get the equation that the voltage induced is equal to the magnetic field strength B multiplied by the velocity V multiplied by the length of the conductor L.